All right, so we've been talking about thermodynamics, and one thing that we talked about the other day was that a change in enthalpy that is positive is indicative of an endothermic reaction. For example, melting, vaporizing, anything along that branch, subliming. In the reverse direction, when you condense, freeze, or if you go directly from gas to solid as you would in deposition, that is an exothermic reaction where delta H is negative. And we talked about change in enthalpy the other day. We talked about how to calculate it and how to interpret it. And that fit into our overarching learning goal as shown here. You're already comfortable with thermochemical terms. You'll see a matching section on it on your test at the end of the week. We'll calculate heat transfer, which you have already done. You also know how to calculate, for example, initial or final temperature. You know how to do calorimetry problems. And you should be comfortable interpreting and calculating changes in enthalpy, that is delta H, change in enthalpy. Today we're going to introduce entropy, which is a measure of disorder in the system, as well as free energy, the energy available to do work, which will determine if a reaction occurs without any assistance. And we're going to talk about thermodynamically favorable reactions, how we determine if the reaction's thermodynamically favorable based on free energy. Thermodynamically favorable or spontaneous processes occur without any assistance. If somebody sprays perfume in the back of the room, those gas particles will diffuse without any assistance. If Like I always have a big cup of ice water on my desk. As the day goes on, the ice will melt. I don't have to do anything to it. If you had hot soup last night and you left it out on the table for a little while before eating it, it will naturally cool. These are all thermodynamically favorable processes. They occur without any assistance. The old nomenclature uses the word spontaneous. The newer nomenclature uses the phrase thermodynamically favorable. You'll see this in newer textbooks, and for those of you who take college or AP Chem, you'll see it there as well. Most exothermic reactions do lead to thermodynamic favorability, but there's another factor to consider, and that is entropy. So not all exothermic reactions are thermodynamically favorable. You need to consider enthalpy, entropy, and temperature. And we're going to link those two, or three actually, together today to talk about thermodynamically favorable reactions. Some endothermic reactions, such as melting, are thermodynamically favorable. So there's more to it than enthalpy. We've got to consider entropy. Now, entropy is a measure of disorder. Disorder in chemistry is a good thing. We're going to take a look at entropy with a few video clips in just a minute. Entropy is a state function. When materials go from high order, which you would see in a solid, to disorder, which you would see in a gas, that is positive entropy, and it often leads to thermodynamic favorability. If, for example, we looked at solids, liquids, and gases, and you've seen this before, but if, for example, we looked at states of matter, for example, water, here's ice, very orderly. Liquid, less orderly or more disorderly. Gas, far less orderly or more disorderly. So one of the things you can see is disorder as you go from solid to liquid to gas. And on this particular diagram that you drew out at the beginning, what you're seeing as you go from solid to liquid, liquid to gas, and so this is going to be disorderly, and that's a good thing in chemistry. Delta S will be positive. This will be orderly. Delta S will be negative. Just remember, Mommy, I want to stay out till 4 o'clock in the morning. No. Negative order. Well, that's how it would be in my house. Got it? All right. So as you go this way, it's more disorderly. This way, it's more orderly. And when you're talking about order and disorder, that's entropy. And there are a few things I want to make sure that you're comfortable with before we really embark on this. So with enthalpy, that's H. And if we look at delta H being negative or less than 0, that's exothermic. Delta H being positive, that's endothermic. If we're talking about entropy, that's abbreviated as an S. Delta S is negative, and that's going to be order. Delta S positive, and that's going to be disorder. You'll see in a little while that the best combination for thermodynamic favorability will be an exothermic reaction that favors disorder. And we're going to add one thing here in a little bit, but we'll just leave it blank for now. Alright, we're going to take a look at a brief video on entropy. I really think it helps in terms of the concept.
We're at Link. We wanted to show you how we created our amazing new website with kids. Now we know that having a great Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 57. It's on entropy, which is really the dispersal of matter and energy. So imagine I had a little bit of milk in a glass and I were to spill it. I will have increased the entropy of this isolated system. And there's an old saying that you shouldn't cry over spilled milk. I totally disagree with this. You should cry over spilled milk. And the reason why is it's an irreversible process. In other words, it's not just going to magically move back into the glass. You increase the entropy and it's going to take a lot of work to put it back where it was. And so entropy in AP chemistry is not something that you'll have to calculate. You have to understand it qualitatively. In other words, you have to look at a system and figure out what's happening to delta S. And so what is delta S? That's simply the change in entropy over time. Now what does this little degree symbol stand for? That means that we're measuring it at standard temperature and pressure. And so if we were to look at a system, we should be able to make predictions about what's happening to our delta S. And that's what I hope you can do at the end of this. And so if we define it, it's simply dispersal. Dispersal of matter and dispersal of energy. So what are some examples of that? Let's say we were to make some phase changes. We were to go from a solid to a liquid to a gas. What would we be doing? We'd be dispersing or moving that matter away from its center point. And so we'd be increasing the entropy. In other words, our delta S would be a positive value. We'd make that matter disperse over time. We also could do that by stoichiometry. In other words, if I look at the moles before a chemical reaction and the moles after, if I have more moles after the reaction, I've increased the entropy. And also, if we take a gas and we increase its volume, we're moving those molecules apart, and so we're increasing entropy, or delta S is going to be a positive value. Now let's say we look at energy. How could we disperse energy? Well, by increasing temperature. If we increase temperature of gas, according to the kinetic molecular theory, we're spreading that energy out and we're increasing entropy. Now entropy is a term that people really struggle with, and so I wanted to start with a good example. And so I've got two videos.
And you really want to watch these videos now because it's tricky until you get the hang of it.
Here, but they're the same exact video. It's just that one of them is played forward and the other is played backward. And so your goal is to figure out which one is forward. So let me start playing that. It's just going to loop over and over and over again. And so your goal is to figure out which one is forward. Have you decided yet? The right answer is
A.
A.
You read from left to right.
Let's look at another one. I've got a little pendulum here, and let me play this video again. It's the same video clip. It's just that one of them is played forward, and the other is the same clip, it's just played backward. Have you figured out which one is forward? There's some clues in here, but the right answer is B. Let's look at the next one. It should be a little easier now. So if we look at the next one, I'm going to play this again. So you can see the forward and backward. Hopefully you figured this out. The right answer is B is being played forward, and A seems somewhat magical. It's being played in reverse. Let's look at the milk. So if we look at the milk right here, which one is being played forward?
Whoa.
Hopefully you figured this out. A is being played forward. Okay, and so why did I do that? Well, what we're looking at here are irreversible processes. In other words, if we play it in this direction, it's irreversible. In other words, it's impossible for it to occur in the reverse. Now, it's not totally impossible. That could occur, but it's statistically improbable that it's going to move in the other direction. And so that direction is really important when we start to talk about entropy, because what happens during an irreversible process is that we're increasing the entropy or the dispersal of that system. And it just doesn't move back, and that'll become really important as we talk about the next few videos.
Now, you can calculate delta S the same way we calculated delta H, or at least similarly. You can do products minus reactions, since entropy, like enthalpy, is a state function. You don't need to know how to calculate delta S in this regard this year, but certainly you could calculate the change in entropy by doing products minus reactants. Again, the only difference is you would use this column. You can see all of these values here are positive. If S is positive, is that order or disorder? Disorder is correct. And you'll also see that whereas delta H, a formation of elements in their standard state, or diatomic elements in their standard state, is 0, that's not the case for entropy. But we're not going to calculate entropy in that regard. I want you to be able to figure out if a reaction is going toward disorder or order based on some of the things he said, and I'll review some of those things here. Keep in mind, we also stated already that as you go from solid to liquid or liquid to gas, you're going to have an increase in disorder, positive. As you go in the reverse direction, it will be negative. Thermodynamically favorable reactions typically show an increase in disorder. Not always, but typically. We'll talk about when they don't. But processes that show positive entropy, and I diagrammed that out for you earlier, I think that will be extremely helpful to you. Again, solid to liquid or liquid to gas. If iodine undergoes sublimation, you're going from order to disorder. That's going to have positive entropy. If you go from liquid to vapor through vaporization, bromine in the liquid state to bromine in the gaseous state, that's going to have positive entropy. If you dissolve a solute in a solvent, in most cases, for example, if you have sodium chloride, which is table salt, and you dissolve it in water, you will have sodium ions and chloride ions, aqueous. You're going from solid, highly arranged, to aqueous, far less arrangement, and so that's going to illustrate positive entropy. There are a few instances where it doesn't. We're not going to focus on that this year. As you heat a system or increase temperature, what happens to particle speed? It will increase. As you increase the speed, you get more and more disordered, so positive entropy. decomp reactions where you have one reactant and more than one product. In addition, you're going from a solid to a solid and a gas. That gets more disorderly. You can have synthesis reactions as well that show disorder. You have solid and gas, and then gases only. This is a tricky one. If you have a reaction in which solids don't change in regard to how many of each you have on both sides of the equation, or liquids, but you see an increase in the number of moles of gas from left to right, that's indicative of disorder. This one's a little tricky. For example, you have 2 moles of gaseous reactant, and 1 plus 3 is 4 moles of gaseous product. You're looking at the coefficients. What is easier for you, to babysit 2 kids or 4 kids? 2, because 4 kids is a whole lot of work because it can be very disorderly. So as you increase the number of moles of gas going from reactant to product, and when you're counting moles of gas, it's coefficient. 2 moles of gaseous reactant, 1 plus 3 is 4 moles of gaseous product. You get an increase in entropy, more disorder. Does that make sense? So if you went, for example, from 5 moles of gaseous reactant, and then you had, let's say, 3 moles of gas plus 1 mole of gas, and this you're applying to gases only, are you getting more orderly or disorderly? You're getting more orderly, because here you have 5 moles of gaseous reactant. Here you have 4 moles of gaseous product. So if you decrease the number of moles of gas without changing other things, you're getting more orderly. As you increase the number of moles of gas from left to right, you're getting more disorderly. So this would be negative. I didn't realize I was so big. There we go. All right, so let's look at this set of equations. This might be something you're asked to do on a multiple choice or even a part 2. It says predict if the change in entropy is positive, favoring disorder, or negative, favoring order. Now I would just ask you, is delta S positive or negative? I wouldn't tell you positive favors disorder and negative favors order. So looking at this first equation, my approach is to first look at the state of matter. And I see I have all gases. So if I have all gases, then I'm going to look at moles of gas. I've got 2 plus 1 is 3 moles of gaseous reactant. I've got 2 moles of gaseous product. So is this illustrating order or disorder? Order. A lot easier to babysit 2 than 3.
Negative.
And this would be negative. Good. Now exo versus endo, be careful. That's different. And that's a common mistake kids make. If I tell you reactions endo or exothermic, that doesn't tell me anything about order or disorder. It's a common mistake that kids make. Iodine gas to iodine solid, are you getting more orderly or disorderly? Orderly, because you're going from gas, which is disordered, to solid, which is ordered. Water in the liquid state to water in the gaseous state,
Disorder.
that would be disorder. And that typically is beneficial for thermodynamic favorability, but you'll consider the enthalpy as well. I look at the state of matter, I have all gases, so what do? I look at the stoichiometric coefficient, 2 moles of gaseous reactant, 1 mole of gaseous product, that is order. This one's kind of tricky, Wiki. This is a reaction that you ran earlier this year. You've got sodium chloride aqueous plus silver nitrate aqueous as well. Aqueous is pretty disorderly, similar to a gas. You're generating solid silver chloride, that's a white precipitate, you've made it, and sodium nitrate, so you're getting more ordered for sure. You generated a solid from two aqueous substances. Does that make sense? I asked you to do a lot of this analysis in your classwork. If you spend the time doing it, you'll nail both of these questions on your test. So, we have talked about enthalpy, exo versus endo. We've talked about entropy, order versus disorder. We're going to link these two with temperature, and we're going to try and figure out whether a reaction is thermodynamically favorable.
So is an aqueous solution like kind of like a liquid solution?
I think it's probably a little more disorderly, and I can't think of a single instance where you would be asked to compare, but a little more disorderly.
So aqueous to solid is orderly?
Absolutely. All right, so we want to figure out whether reaction is thermodynamically favorable or spontaneous. We've got to consider enthalpy, entropy, and temperature. And the way we do that is through Gibbs free energy, abbreviated with a G. This is how much energy is available to do work. It takes enthalpy, entropy, and temperature into account. There are a number of ways to calculate delta G. Gibbs free energy is a state function, so you can do it the same way we calculated delta H, where this time you would be focusing on this middle column. I'm not going to have you calculate it in that regard. Rather, we're going to use the formula highlighted in yellow, where you have delta G is equal to delta H minus T delta S. And you took your quiz and you saw that formula at the bottom, and some of you were like, oh my God, we didn't learn that yet. Yes, I know you didn't learn that when you took the quiz. I just had one card with all the formulas, and it knew it was coming right here. Couple things you need to be very careful of when you use this formula, and we're going to go through this in detail. But what you're going to see, and I'll mention it several times because it's a common mistake that kids make, delta G for a reaction under standard conditions is delta H minus T delta S. Delta H is going to be in kilojoules or kilojoules per mole. The temperature will be measured in degrees Celsius, but you better convert it to Kelvin. What do you add? 273.15. Delta S will be in joules per mole Kelvin or joules over Kelvin, and you must make a conversion from joules over moles Kelvin to kilojoules over moles Kelvin. And that you can achieve by dividing by 1,000 or moving the decimal 3 to the left. Remember, 1 kilojoule is 1,000 joules. I mention this here because the units become problematic. You'll get the Kelvin to cancel, and then when you subtract this, you'll have kilojoules per mole. Be very careful here. This is the common error, and if you don't use the conversion, your answer will be incorrect. Be very careful there. With that said, before we work through some of the problems, I want to show you a brief video on Gibbs free energy. It's going to show you the linkage between enthalpy, entropy, and temperature. So let's take a look.
Hi, it's Mr. Anderson, and welcome to my podcast on Gibbs free energy. Whenever I get to Gibbs free energy in the year, I can see my kids' eyes gloss over and they're confused. And even William Gibbs talks about this in this quote. He said, "The idea of entropy and the second law of thermodynamics will seem far-fetched and may repel beginners as obscure and difficult for comprehension." So what does that mean? I'm going to try to tackle something that's been a problem for years. I'm going to try to make Gibbs free energy more understandable. And so that you really know what it is and understand the power of it, especially in biology. And so I think the first place to start is the name itself. The idea of free kind of gets in the way. And so what I'd like to go back to is the old name, which it used to be called available energy. And so let's think of delta G as available energy, or energy that we can actually use to do work. The other thing that I think makes it hard is the equation itself is confusing. We've got delta G, we've got enthalpy, we've got entropy, we've got words that you're maybe not understanding. And so what I'm going to try to do is pare this down to the easiest explanation that I can, and then we can get into more of the specifics a little bit later. And so the best place to start when you're trying to understand available energy or free energy is to look at spontaneous reactions. Spontaneous reactions are reactions that once you give them a little bit of a push, they'll actually go on their own. These reactions also will tend to release energy, and they give energy to their surroundings. Quintessential example in life is cellular respiration. But let's not get there yet. So the three reactions that I'm going to talk about here are, number one, a ball rolling down a slide. Number two, diffusion. And then number three, a cherry bomb that's exploding. And so we're going to apply Gibbs free energy to each of these. So let's start with the ball at the top of the slide. And the ball at the top of the slide is going to roll down to the bottom. And so the first thing that I want to give you is what's called enthalpy, or total energy of a system. And so if we say this is a system, what happens to the total energy of the system as the ball rolls down the slide? Well, if you know anything about potential energy, the amount of potential energy that we have up here is going to be greater than the amount of potential energy that we have down here. And so the total energy of the system, we'll call that H, or enthalpy. The total energy of the system has gone from a big H to a little h. In other words, the total energy of the system has decreased when the ball rolls down. Now, if I had to push it up again, then we would add energy to the system. But this is a spontaneous reaction, and the enthalpy, or the total energy, is decreasing. Now, in biology, we don't move around because of potential energy or mechanical potential energy. In biology, our energy, or our potential energy, is actually in these bonds. In other words, there's a huge amount of potential energy in this bond between the carbon and the hydrogen. And so this right here is glucose. And if we can release some of that energy, we can do it to do work. And so again, what is H? H stands for the total energy of the system. And it looks like in a spontaneous reaction, that's actually going to get smaller, or decrease. Okay, next one, let's talk about diffusion. So in diffusion, imagine that right here we've got a bunch of molecules in this container, and they're bouncing around, and I remove this wall. So if I remove that wall, what's going to happen to the molecules? The molecules are going to spread out to fill that area. We call that diffusion. Now, entropy is, we use the symbol S for that. Entropy is a measure of the disorder of a system, or sometimes we call that the randomness of the system. And so let's compare this. Right here we've got a bunch of molecules on this side, and then we've got a lot of space over here. So what happens to the disorder of that system as I do diffusion? Well, it's becoming more disordered. In other words, the entropy is increasing. What's an example of that? Let's say I go into your room and your room's a mess. It looks like this. If I say clean up your room, then you can go like that. And so what happens through diffusion, or in this spontaneous reaction? Well, let's say remove this wall. What's going to happen now? We're going to get even more disorder. So we're going to even get a bigger S value. And so in this spontaneous reaction, it looks like the S value is increasing. Okay, the last one is that cherry bomb. So let's say we have a cherry bomb, put it on the desk. Does it explode? No. And one of the reasons it doesn't is the temperature is really low. And so let's say I add a bonfire to the situation, so I increase the temperature. Does that make it a more spontaneous reaction? Is the reaction more likely to happen or less? Well, it's more likely to happen if I increase the temperature, more likely to get an explosion. Okay, so those three things, total energy or enthalpy, entropy or S, and temperature can affect spontaneous reactions. And so now let's apply that to Gibbs free energy. And so before we actually get to the equation, let's just do a little algebra here. So let's say I wrote this equation, x equals y minus ab. Okay, so let's say we had this equation right here, and I were to decrease this value, the y value. What would that do to the x value? It would decrease it, right? Let's say I were to increase the a value and increase the b value. What would that do to the x value? Well, since we're subtracting right here, that would decrease it as well, or make it even go farther down. And so let's go back and summarize those three spontaneous reactions. In the first one, the ball rolled down. So what happened to our H value? Well, our enthalpy of the system decreased. What should that do to our Gibbs free energy or available energy? It should decrease that value. What happened here when we increase the entropy of the system? We increase the delta S. Well, if we increase the delta S, that should also decrease the Gibbs free energy. So now we have two things decreasing that. And what happened here? Well, if we increase the temperature, that made it more spontaneous. So if we increase that, we also decrease the Gibbs free energy. So what's the moral of the story? Moral of the story is that if the delta G ever decreases, or if it's ever less than 0, that's a spontaneous reaction. Likewise, if the delta G is greater than 0, let's turn to the next slide, that's going to not be a non-spontaneous reaction.
And he did a very good job with that analysis there. We're going to take it a step farther in just a few minutes. But I want to show you how to calculate delta G, the change in Gibbs free energy, and that will tell us the energy available to do work. So we're going to walk through these two examples. In the first example, actually directions are the same for both. Calculate the Gibbs free energy delta G for the following reactions. Indicate whether the reaction is thermodynamically favorable. Justify your answer. Before we do that, let's finish out this table here because I think it will be extremely helpful to you. So what we're looking at here is this is going to be free energy and this is G, and when it's negative you've got a thermodynamically favorable reaction, and when it's positive you've got a thermodynamically unfavorable reaction. And that'll be the last piece of the puzzle. And I had said to you earlier that an exothermic reaction that illustrates disorder would lead to a thermodynamically favorable reaction, and that's what he was talking about there. On the flip side, if you have an endothermic reaction that illustrates order, that will always be thermodynamically unfavorable, and we'll talk about that in a little bit. But this little piece right here will help you greatly put these concepts together. All right, so what we want to do now is we're going to use this equation to calculate delta G. And in the first example provided to you, in your notes, you've got an equation. We want to know delta G, and we want to know if it's thermodynamically favorable and why. They told us that delta H is 140.5 kilojoules per mole. Is that endo or exothermic? Endo. And they're telling us that delta S is negative 38.9 joules per mole Kelvin. And the temperature is 25 degrees Celsius. So all of that is given. We know that delta G is equal to delta H minus T delta S. I've got 140.5 kilojoules per mole minus the temperature must be in Kelvin. Add 273.15, you get 298.15 Kelvin. Don't forget to convert degrees Celsius to Kelvin, just like we did in our gas law chapter. The other thing you need to be very careful of is you need your entropy to be in kilojoules per mole Kelvin, and you will achieve that by dividing by 1,000 or moving the decimal 3 places to the left. Now it just becomes a plug and chug situation. You've got 140.5 minus 298.15 times negative 0.0389. In regard to my Siggy Wiggies, I usually will look at decimal places for my delta H. It almost always works. It'll be easy for you to do. 152.1 kilojoules per mole. Keep in mind the Kelvin cancel. So 152.1 kilojoules per mole. So the reaction is not thermodynamically favorable. You got it, because delta G is positive. And as I alluded to previously, a reaction that is both endothermic and favors order will never, ever, ever be thermodynamically favorable. The keys to being successful on these problems: make sure your temperature is in Kelvin. Make sure you convert delta S to kilojoules per mole Kelvin. Otherwise, you can't subtract the quantities. You must have the same unit in order to subtract quantities. Before doing the second problem, which is a little more involved because you have to find delta H first, I want to go through the information at the end here. We had these two combinations already. If you have a reaction that illustrates disorder and is exothermic, the reaction will always be thermodynamically favorable. If the reaction illustrates order and is endothermic, it will never be thermodynamically favorable. And this is as he illustrated to you. From this equation, you can see in an exothermic reaction that favors disorder, a negative minus a positive will always give rise to a thermodynamically favorable reaction. In contrast, in endothermic reaction that illustrates order, a positive minus a negative will always give rise to a thermodynamically unfavorable reaction. And the question becomes, well, what if it's exothermic and illustrates order? Then it tends to be a little more complicated. If, for example, you had an exothermic reaction that favored order, the way you could get a thermodynamically favorable reaction is if this term predominates. This term will predominate when the temperature is low. On the flip side, if you have an endothermic reaction that illustrates disorder, the only way you can get a thermodynamically favorable reaction would be if the temperature is high. So at low temperature, the enthalpy term predominates, and that's in your notes. At high temperature, the entropy term predominates. But you really want to be most comfortable with this, a simple interpretation of thermodynamic favorability from here. And we'll give some additional examples of this next time. I'll open up with a do now on it prior to you really working on the classwork for this. You can now complete your classwork, and I'm going to leave you with, I'll put the answer on the screen, but I'm going to leave you with this second problem to do. I want to make sure you can calculate delta G with ease. This problem's a little more involved because I didn't give you the delta H. Do you know how to calculate delta H? Yeah.
Yes.
So calculate delta H first, and then calculate delta G and interpret it. And spend a good 5 to 7 minutes on this. This is exactly how your test will play out, where I'll ask you to calculate delta H, and then you'll use it to determine delta G. Question?
For delta S, how would you change like the units?
To go from joules per Kelvin to kilojoules per Kelvin, you simply move the decimal 3 to the left or divide by 1,000.
Or when do you need it over kilojoules over moles?
In this particular problem, you don't need it per moles because when you calculate the delta H, it'll come out in kilojoules. Give number 2 a try. I'm going to work it up on paper. You try it. Number 2 off the screen. Give it a shot. And you have those delta H's of formation. And on this one, you can find everything off the back of your periodic table. Make sure you do products minus reactants. Also, make sure you grab water in the gaseous state, common mistake made. Anybody have a delta H value yet?
Good afternoon, Cobras. Please listen carefully to the following announcements prior to this event of striking today. Attention Algebra 1 students. The Algebra 1 lunchtime reviews will start today at lunchtime in room 4107. Biology students. Biomania review for the Biology EOC is taking place again today during lunch in room 3101. Please report to room 3101 at the beginning of lunch and enjoy Biomania. Attentional geometry students, come join us today in room 6113 for the first EOC Power Lunch. Feel free to bring your lunch and immerse yourself in some awesome geometry proofs. A friendly reminder, Cobra Link Crew applications are due to Ms. Lamb in room 4108 by Friday, April 13th. And hey Cobras, are you hungry? Are you thirsty? All Gatorade products are on sale today in the courtyard. Come get a free Park Vista water bottle with your Gatorade chews, drinks, shakes, or bars. Yes, you heard it, Cobras. It's free is the key word. See you in the courtyard at lunch, and please do not forget to see our prom fashion show, which will be the highlight of today's lunchtime. Teachers, at this time, please turn on your computers and prepare for this afternoon's video announcements. This Venom strikes now.
Who's got a delta H for me? What do you got, Austin? Negative 2043.1 kilojoules is delta H. And what do you have for delta G? Close.
Close? So negative 2,237.6? Or just that? Just that point two?
This is what I got. Negative 2,237.0 kilojoules. This reaction is in fact thermodynamically favorable with a negative delta G, which you would predict from an exothermic reaction that illustrates disorder. And you have several problems like this on your classwork. The more you do, the more likely you will increase your success for your test. Please don't wait until the end of the week. You need to do them, and then you need to do them again. Questions here? All right, so enthalpy, entropy, and temperature all tie into free energy, and that will determine thermodynamic favorability.